Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 24 on the subject of computer organization and assembly language programming. The title of today's session is Design of Hack Computer. Alhamdulillah, all praises to Allah. Today we are finally going to write the HDL of the hack computer, which we started 23 lectures back. Today we are going to start with a quick recap of the hack computer architecture. We are going to write the HDL for our hack CPU, its data memory and instruction memory using the chips that we have designed in this course. And then we will use these three chip parts to build the complete hack computer. At the end of today's session, we will load the HDL file of our hack computer inside the hardware simulator, and we'll load and execute different assembly programs in our hack computer. So we have a lot to do today. Let's start playing. Dear students, most of you must be knowing about, but let me repeat again a few words about the hack computer architecture. This must be boring for some of you. But one of my teachers once told me that our teacher is someone who always repeat. So let me repeat. So this is a bigger picture of our hack computer, which is a 16-bit von Neumann machine designed to execute programs written in hack machine language. It consists of a CPU, two separate memory modules serving as instruction memory and data memory, and two memory mapped I/O devices, a screen and a keyboard. In the last session we have seen all the theoretical and design aspects of the hack CPU. And before we write the HDL for this hack CPU, let us quickly have a recap of the hack CPU interface and connectivity of its chip parts. Well, this slide shows the hack CPU interface. On the left hand side you can observe that it has three inputs coming from completely different sources. 16-bit in M coming from the data memory, 16-bit instruction coming from instruction memory, and a single bit reset input. On the right hand side you can see four outputs. 16-bit out M, which is the computational result generated by this ALU. This 15-bit address named address M, and a 1-bit write M. So these three outputs together are going to write this value inside the data memory at this address, provided if this write M single bit output is set to 1. The fourth output is a 15-bit address of the instruction memory, and this is the address of the next instruction to be fetched and executed by the CPU. And this slide shows a more detailed view of our hack CPU with all the chip parts and how they are connected with each other. Well, there are three registers, A, D and PC, two MUX16 chips and an ALU chip. In the last section we have seen in detail as to how the information move among these various chip parts inside this hack CPU. Dear students, the tricky part in writing the HDL for our hack CPU is handling and routing different control inputs. As you can see, a control input for this MUX16, for this MUX16, the control input for these three registers, and the control input of course for this ALU. So two control inputs for these MUX16 chips, three control inputs for these three registers, and six control inputs for the ALU specifying the operation it needs to perform. So let us now understand how these different control inputs can be routed to appropriate chip parts. and let me start from the select input of this MUX16 chip, which is responsible for selecting the input of this A register out of these two possible values. Well, dear students, you can observe the most significant bit of the instruction is used as the control input to this MUX16 chip. And we all know that for an A instruction this will be 0, so A register will get its input from the instruction part of the memory, that is the remaining 15 bits of the instruction. And for a C instruction this will be 1, so A register will get its input from the ALU output. So I think this control input to this MUX16 is clear. Let's move ahead and talk about the control input of the second MUX16 chip, which is responsible for the second input of the ALU out of these two possible values, one coming from the A register and the other coming from the data memory. Well, dear students, please recall this computation table which we have used while designing the hack machine language. The 6 C bits from C1 to C6 specify the ALU operation, and the 7th bit A over here specifies whether you want to do that operation on the A register or on the memory. Note that for A is equal to 1, the operand is from the memory, as you can see the M's over here, and for A is equal to 0, the operand is from the A register. And these 6 or 7 instructions can be seen over here as well, inside the general format of a C instruction. So the control is very simple. We simply feed this select input of this MUX16 chip with the 12th bit of the instruction, which is this A over here, and which is this A over here. So if this is 0, that means the ALU will get its input from this A register, and if this is 1, that is this instruction bit number 12 is 1 as shown over here, that means the ALU will get its input from the memory. Okay, so now we are done with the control input of the two multiplexer chips. Let's talk about the load inputs of the three registers one by one. And let us first talk about the load input of the A register. Well, this A register needs to be loaded in two situations. First is if the instruction is an A instruction. So if this is an A instruction, let's suppose this is an A instruction, so we will have a 0 over here. That means this A register needs to be loaded. And second is if this A register is the destination register for a C instruction. So this is the destination table. From this table you can observe that A register is destination register for these last 4 rows only, because for these last 4 rows this A register is the destination, and we have this D1 bit set as 1 over here. So the load input of the A register can be set to not of 15th bit of instruction with a bitwise OR of this D1 bit of the destination field, that is instruction number bit number 5 of the instruction, this one, this D. I hope this makes sense. If not, please revise this part and watch again. And let me move on to the load input of the D register chip. And for this we need to find out the different scenarios when this D register is the destination register. And once again the table for the destination field of C instruction will come for our rescue. And in this table you can observe that whenever D register is the destination register, the D2 bit is 1. So D2 bit is 1, D is the destination, D2 bit is 1, D is the destination, and over here as well. and this D2 bit is of course this bit of the instruction, that is the fourth bit, 0, 1, 2, 3 and 4. So this is the fourth bit. So it's very simple. We simply load the D register whenever the bit number 4 of the instruction is 1. So we are done with the control input or load input of the A register. We are done with the load input of the D register. Now let's talk about the program counter. And we all know that program counter will be loaded from the contents of this A register as shown over here. And this will happen only in case of a jump. And this time the table for the jump field of C instruction will come for a rescue. Well, dear students, if all the 3 jump bits are 1, the PC register will be loaded with a new value. So if all these 3 are 1, this will be loaded with the value present inside the A register. Otherwise, we will in these remaining 6 scenarios, we will check for this ZR and we will check for these ZR and NG output bits of the ALU. Okay, so I'm sorry for this. So we will check for these ZR and NG bit output bits of the ALU, and if the jump bits and this 0 bits together decides that a jump should be taken, only then the contents of A register will be placed over here. So this control load input will be set only if this function returns 1. And I think I have talked about this in a previous session as well. So once we are done with the control input of the program counter, let's move on to the control input of the ALU. Well, for this we see the table of the computational field of C instruction as shown over here, and these are the 6 C bits that are going to decide about the operation the ALU needs to perform, and these 6 bits are in the instruction from bit number 6 to 11. So instruction number 6 to 11 are placed over here. So this is the control input of the ALU. Okay, so we are done with the complete design of the hack CPU, and now this slide shows the CPU.hdl file. You can see the CPU chip interface diagrammatically over here, and over here inside the code you can observe that the CPU chip interface has 3 inputs and 4 outputs, and this we have discussed in length today. And this slide shows the complete chip implementation, and after such a long discussion I think this code will certainly make sense to you all. You can note the 2 MUX 16 chips. You can note the A register, D register and the program counter chip. Also note the ALU chip. And the rest of the code is all about the control inputs of different chip parts. Dear students, one more point I want to make is that all these chip parts, starting from this NOT gate at the top to this program counter chip at the bottom, we have designed each and every one of these chip parts in the previous lectures. So there is nothing new other than the design logic. Okay, so dear students, we are done with the hack CPU, and we are done with the hack CPU, and we are left with the memory and the instruction memory. And now let us write down the HDL for our hack memory chip. And before I show you the just 5 lines of code for this chip, let me quickly recap what this memory chip is composed of. Well, dear students, this is the overall address space known as the hack memory, and this chip is essentially a package of 3 16-bit storage devices, a RAM chip, of 16K registers, each register of 16 bits, a screen chip of 8K registers acting as a screen memory map, and a keyboard chip of only one register acting as a keyboard memory map. And let us review the HDL of these three chips one by one. So this is the HDL of the RAM 16 chip that we designed and wrote in lecture number 12, I think. It consists of 16K registers. So over here we have 16K registers, each register 16-bit wide, and from this chip interface you can observe that it has three inputs: 16-bit data input named in, a single bit load enable named load, and a 15-bit address. If the load input is 1, then this in value is written in the memory specified by this address. Moreover, it has a 16-bit output named out, which will always emit the 16-bit contents of the currently selected register. Also note that in this overall memory chip, this RAM 16 chip has addresses ranging from 0 to 16383. Now let us talk about the screen chip. We have seen that the display unit of our hack computer consists of 256 rows and each row having 512 columns, thus making a total of 131072 black and white pixels. And this screen is interfaced with the hack computer using memory mapped I/O technique. Over here you can see the screen chip interface. It functions exactly like a 16-bit 8K RAM. And instead of writing our own HDL for this chip, we will use the built-in screen chip, whose HDL is shown over here, featuring a raster display refresh side effect as well. The address mapping of the screen chip in the overall memory chip range from address 16384 to 24575, making a total of course 131072 bits. Dear students, we have studied in detail as to how each of these 131072 bits in the screen memory map are mapped onto the 131072 pixels on this physical screen. Whenever we want to make pixels on or off on this physical screen, we set or reset the corresponding bits inside this screen memory map. And of course, in the next refresh cycle, the updated screen memory map contents are refreshed on the physical screen. Okay, so this is finally the keyboard chip, and we also discussed this chip in lecture number 18. The only input device that we have interfaced with our hack computer is the keyboard. And once again, instead of writing our own HDL for this chip, we will be using the built-in chip, whose HDL we have seen and practiced in the previous session. You can see there is no input and only one 16-bit output, and of course that will be the ASCII code of the key pressed by the user. You can see this and understand it over here as well. Well, this built-in keyboard chip has a read-only register, 16-bit register, and of course it has a keyboard input side effect as well. It will get connected to the physical keyboard of our machine, of our host machine. Since at any instant of time the user is supposed to press only one key, so we only need just one register to store the ASCII of that key. Well, this keyboard is also interfaced with the hack computer using the memory mapped I/O technique, and since we need only 16 bits, so the address map of this keyboard in the overall memory chip is 24576. So to summarize, whenever a program wants to read the key pressed by a user on the keyboard, it will simply read the 16-bit word at memory address 24576. So finally, this is the overall memory chip implementation of our hack computer. And to describe it in simple words, it is a memory having 32K 16-bit words. It always outputs the 16-bit value stored at any of this memory location specified by this 15-bit address. And if this load input is 1, this 16-bit in value is loaded into the memory location specified by this address. And moreover, the new value written becomes available at the output of this chip from the next cycle onward. And as far as the address space is concerned, the first 16 K addresses are used for general purpose data 0 to 16383. The next 8 K addresses are used for the screen memory map 16384224575. The address 24576 is used for the keyboard memory map, and access to addresses beyond 24576 are considered invalid. Well, if you see the HDL code, the chip interface part is clear. And let's review the implementation part. First of all, we have 1/2 demugs. Well, if bit number 14, that is the most significant bit of the address, is 0, that means we need to load or write the data memory. And on the contrary, if this bit number 14 of the address is 1, that means we need to load or write the lower half of the memory or the screen memory map. So these are the two outputs of this mux. In case if this is 0, that means we want to load the RAM, that is this 16K RAM. If this is 1, that means we want to load the screen. So this is the task of this demultiplexer. Next line of code uses a RAM 16K chip. Just note the address part, which are the initial 14 bits of address, and also note the load input of this RAM 16 chip, which is the load RAM output of this demux. Similarly, next line of code is the built-in screen chip. Over here, note the address part, which is the initial 12 bits of the address 0 to I think it should be 11 over here, I don't know. Also note the load input of this screen is the load screen, which is the output of this demux over here. And finally, we have the keyboard and this mux 4-way 16 chip, which will decide which out of these three chips, RAM 16, screen and the keyboard, should be allowed to place their 16-bit outputs on the actual 16-bit output of this overall memory chip. So we have this mux 4-way 16 somewhere over here, which will decide whether to write the output of this RAM over here, this screen over here, or of course this keyboard over here. Although this keyboard is not to be read. So anyway, if I go into a bit of details, you can see this address bit 13 and 14 over here. These are the select input of the mux 4-way 16. If these 13 and 14 bits are 00 or 01, if these two are 00 or 01, this final output will be the output of the RAM chip. If these two bits are 10, the final output over here will be the output of the screen memory map. And if these two bits are 11, the final output will be the output of the keyboard memory map. Well, dear students, I have tried to describe this overall memory chip implementation in the maximum possible detail. might have become boring for some of you, but anyways, please do write this code and implement it on the hardware simulator. And let me move ahead. So finally we are done with the writing and understanding the HDL of our hack CPU chip and memory chip, and now is the time to talk about the implementation of this instruction memory or the ROM chip. And once again, instead of straight away jumping onto the HDL code, let me spend a few minutes on the functionality of this ROM chip. So this slide shows the task of the instruction memory, and that is load this hack machine program into the instruction memory. Then we press this reset button and the program starts running. It's simple. Now $100 question is, how do you load a program into this instruction memory? Well, there are two options. First is the hardware implementation, and for that we use specialized hardware, normally called the programmers, which burn or write the hack machine code into a EEPROM chip. We then plug that EEPROM chip into the computer, press the reset button, and our program starts running. And if you want to run another program, you repeat this process. And this process you might have seen in case of the game cartridges for the game consoles. And the other is the hardware simulation, which we are going to use in this course. Programs are stored in text files, and program loading is emulated by the built-in ROM chip. So this ROM chip will have the functionality of loading an assembly program into it. And this slide describes the ROM 32K built-in chip in a bit of detail. Well, the hack instruction memory, ROM 32K, is actually a read-only 16-bit 32K RAM chip with the program loading side effect. This chip always output the value stored at the memory location specified by this address, which is the next instruction to be executed. The built-in chip implementation written in Java has a GUI side effect showing an array-like component that displays the ROM's contents as well. We will soon see it in a demo. And this ROM 32K chip is supposed to be preloaded with a machine language program. However, once we will load this inside the hardware simulator, it will allow the user to load the hack machine program from a hack file. Okay. So dear students, now is the time to integrate all these chips to write the HDL of complete full-blown hack computer chip. And this slide shows the abstract view of our hack computer. And so to implement our hack computer, we just need 3 chips. The CPU chip having 3 inputs, a 16-bit instruction coming from the ROM 32K chip, a 16-bit operand coming from this memory as shown over here, and a single bit reset input. Then it has 4 outputs, a single bit load enable, 16-bit out M or write M, and then we have the 15-bit address input. And finally we have the 15-bit address of the next instruction inside this PC, which is going to this ROM 32K. And we already have built the memory chip, which is further composed of a 16K RAM chip, 8K screen chip, and a single register keyboard. Similarly, we have built the ROM 32K chip as well. So all these tasks are done. So the task left is to integrate all these 3 chips to build our full-blown hack computer. And my dear students, this slide finally shows the just 3-line HDL code of a full-blown 16-bit hack CPU, capable of executing hack machine program residing inside the ROM 32K chip. When the reset input of the computer chip is set to 1, the program starts its execution from the very first instruction. Moreover, depending on the program's code, the screen may show some output and the user may be able to interact with the computer via keyboard. So let me once again say that writing HDL of a full-blown computer with just 3 lines of implementation code is simplicity at its peak. Okay, so before I close, let us now load HDL code of this hack computer chip in the hardware simulator and see how can we load and execute hack machine programs in this computer chip. Let us move on to the terminal and run the hardware simulator. Hardware simulator is running. Let me adjust the screen and let us load the Computer.hdl chip. So this is the Computer.hdl chip we have designed today. Dear students, note that in this directory, the lecture number 24 directory, we have the HDL code of just 3 chips: Computer.hdl, CPU.hdl and Memory.hdl. The ROM 32K.hdl, Screen.hdl, Keyboard.hdl and all the other constituent chips like A register, D register, Mux16 and so on are not here in this directory. Well, the hardware simulator will search all those chips whose HDL files are not here in this directory in the built-in subdirectory of the tools directory. Another option is, since we have designed all those chips in this course, so we can place the HDL files of all the required chips in this directory. So the hardware simulator in that case will not use the built-in version, rather will use the HDLs of our code that we have written. Anyway, let me load this Computer.hdl by clicking this load chip button, and wow, great. So this is it. Let's have a review of the GUI component. In the top left corner over here, you can see the chip name, that is computer. The only input pin is the reset bit. If you review the HDL code in the HDL pane, the implementation part shows just 3 lines of HDL code: the ROM 32K chip, CPU chip and the memory chip. Out of these 3 chips, observe the GUI side effects of the CPU chip over here. This is the ALU getting its 2 operands, one from the D register and the other either from the A register or the memory, and this is the M mnemonic representing the active memory register. You can also see the 3 CPU register: A register, D register and program counter register. Well, above this on the right you can see the program or the instruction memory, the ROM chip, which do not have any program loaded inside it right now. The other chip is the RAM 16 chip. This memory chip consists of the RAM 16 chip, and above that we have the physical screen 256 rows, 512 pixels, and interfaced with the overall memory chip using the memory map technique. And finally we have this keyboard chip as well, which is attached with the keyboard of our system. Okay, so I think the GUI is quite familiar to you now. Let us load a hack assembly program in our hack computer and run it. And for that I need to load the program inside my instruction memory by clicking this button. And let me search for that location where I need to go. Okay, so lecture codes, inside lecture codes 24. Okay, so there are a lot of assembly programs which we have written. Let me load the rectangle.asm program. Okay, so this is the code for the rectangle.asm program. Just 24 lines of code, you see. Well, this program actually draws a filled rectangle at the upper left corner of the screen. The width of the rectangle is fixed, that is 16 pixels. while the height is specified by the number written at this RAM address 0. We do ran this program before as well. Let me write down 50 over here so that I get a rectangle over here having 16 pixels wide and 15 rows down. So let me adjust the speed of the slider. Let me move it to a bit fast, and let me execute the program by clicking this run button. So this program has started running. Keep observing the contents of the program counter, different registers, and keep noting over here this rectangle will start growing down. Let me move its speed a little more, and you see this is growing down. That is great. Let me stop the execution of this program. My dear students, I strongly recommend that you should run all of the hack assembly programs that you have written in the previous sessions on this hack computer instead of the CPU emulator now. And let me fall back to the slides. Okay, so that is it, dear students. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning, and Allah Hafiz.